Hi students, in this video I am going to talk about some important probability distributions that are heavily used in statistical methods. Okay, student T distribution is simply called T distribution. Why this name? Because it was published under the name student T. Let x and y are two independent random variables. Here x is a standard normal random variable, y is the chi-square random variable with n degrees of freedom. Then t equal to x by root y by n. You can also write like root n x by root y. Here this t is said to have student t distribution on n degrees of freedom. Okay. Now let us try to see PDF of t. Here this t look like a g of xy. We know how to find out the PDF of the random variable, which is a function of x and y. What do? You take one transformation t equal g of xy and introduce another auxiliary transformation like a u equal to y. Then we find out the giant PDF of tu in terms of giant PDF of xy and the Jacobian of the transformation. Okay. Then we get the PDF of t as a marginal PDF of tu like this. Okay. Fine. Okay. First of all, we need a giant PDF of xy. Okay. Here x is a standard normal random variable, y is a chi-square random variable on n degrees of freedom. So the PDF of x going to be fx of x equal to 1 by root 2 pi e power minus x square by 2 for minus infinity less than x less than infinity, and the PDF of y, fi of y equal to 1 by 2 to the power of n by 2 gamma n by 2 times y to the power of n by 2 minus 1 e power minus y by 2 for y positive. So 0 otherwise. Okay, this is the PDF of y. Okay. Now the giant PDF of xy going to be PDF of x times PDF of y, since x and y are independent. Okay. So to get the giant PDF of xy, simply let us multiply these two PDFs. Okay. So this is what we get. Here root 2 times 2 to the power of n by 2, I can write 2 to the power of n plus 1 by 2 in the denominator, and we have a root pi gamma n by 2 and this y to the power of n by 2 minus 1 and e power minus x square by 2 times e power minus y by 2, I can write e power minus 1 by 2 of y plus x square. Okay, for minus infinity less than x less than infinity and y positive, obviously 0 otherwise. Okay, this is the giant PDF of xy. Okay, fine. Now consider the transformation t equal to root n x by root y and auxiliary transformation u equal to y. Now this transformation t equal to root n x by root y, u equal to y can be uniquely solved for x and y like this. X equal to t under root u by n and y equal to u. Let us find out the Jacobian of this transformation. Jacobian of this transformation going to be determinant of this 2 by 2 matrix. Here this dou x by dou t going to be under root u by n. Okay, dou x by dou u I'm not going to care because dou y by dou t going to be 0 and dou y by dou u going to be 1. So data of this matrix going to be root u by n times 1 minus 0 times dou x by dou u. It's going to be root u by n. Okay, Jacobian of this transformation is under root u by n. Fine. Now the giant PDF of tu in terms of giant PDF of xy and the Jacobian of the transformation is this. F tu of t comma u equal to fxy of t under root u by n comma u times modulus of the Jacobian. Okay. Okay. So the Jacobian of the transformation that we got under root u by n. Okay. Now to see this, we substitute t under root u by n for x, u for y in the giant PDF of xy. So we will have this. 1 by 2 to the power of n plus 1 by 2 root pi gamma n by 2 times u to the power of n by 2 minus 1 times e power minus 1 by 2 of u plus t square of u by n times modulus of the Jacobian of the transformation, that is root u by n. Okay, so now this gets simplified to, so 1 by 2 to the power of n plus 1 by 2. If I write this root n here times root pi gamma n by 2. Okay, here u to the power of n by 2 minus 1. Here we have a root u that I can write u to the power of n plus 1 by 2 minus 1 e power minus u by 2 of 1 plus t square by n. Okay, this is the giant PDF of TU. Okay, so this is the giant PDF of TU for minus infinity less than t less than infinity and u positive, so 0 otherwise. Okay, fine. Okay, now we are going to get the PDF of t as a marginal PDF of TU. So to find the PDF of t, we integrate the giant PDF of TU with respect to u from minus infinity to infinity. But here u positive, so it is enough to integrate from 0 to infinity. Okay, so here we are integrating the giant PDF of TU with respect to u from 0 to infinity. This is kind of a constant, so I'm writing out of the integration, right? Okay, now we have to integrate this one. Let us make a substitution here. S equal to u by 2 of 1 plus t square by n. Now that implies ds equal to 1 by 2 of 1 plus t square by n du. Okay, from this relation I can write u equal to 2s by 1 plus t square by n. And with this relation, S limits are also going to be from 0 to infinity. Okay. Now the PDF of t at t is going to be 1 by root n 2 to the power of n plus 1 by 2 root by gamma n by 2. Now this integral I can write integral 0 to infinity. This one I am replacing with s. So e power minus s and u got replaced by is 2s by 1 plus t square by n. So I am writing 2s by 1 plus t square by n all to the power of n plus 1 by 2 minus 1. And this du got replaced by ds by 1 by 2 of 1 plus t square by n from this. Okay, fine. Now this gets simplified to, if I write things not involving s out of the integration, here we have a 2 to the power of n plus 1 by 2 minus 1. Here we have 1 by 2. So total I can write 2 to the power of n plus 1 by 2 out. Okay. And in the denominator we have a root n 2 to the power of n plus 1 by 2 root pi gamma n by 2. Here we have a 1 by 1 plus t square by n all to the power of n plus 1 by 2 minus 1. Here we have a 1 by 1 plus t square by n. Total I can write 1 plus t square by n all to the power of n plus 1 by 2. Then integral 0 to infinity e power minus s to the power of n plus 1 by 2 minus 1 ds. Okay, fine. Now this look like a gamma integral. This one I can write gamma n plus 1 by 2. Fine. Okay. Okay. So this is the PDF of t at t, and this is going to be gamma n plus 1 by 2. Okay. Now this gamma n plus 1 by 2, let me write like a gamma n by 2 plus 1 by 2. This 1 plus t square by n all to the power of n plus 1 by 2. I am writing in the numerator like this. Okay. Now this root pi got replaced by gamma of. Okay. So gamma of value root pi. Now if I write this one in the denominator, gamma n by 2 plus 1 by 2, so whole thing I can see as a beta function, right? Okay. Now we have ft of t equal to 1 by root n beta of n by 2 comma 1 by 2. It's a beta function of 1 plus t square by n all to the power of minus of n plus 1 by 2 for minus infinity less than t less than infinity. Okay, this is a PDF of t distribution with the n degrees of freedom. Okay, fine. Okay, here is the notation. We read it as t follows the t distribution with n degrees of freedom. Okay, now the properties, you can see that this ft is symmetric about 0 because it's the even function. As you can see, ft of minus t is same as ft of t, which is even function, so this is going to be symmetric about 0. Next, for n equal to 1, if I take n equal to 1, this PDF will turn out to be 1 by root 1 beta 1 by 2 comma 1 by 2 1 plus t square by 1 all to the power of minus of 1 plus 1 by 2. Now this beta 1 by 2 comma 1 by 2 going to be what? Beta 1 by 2 comma 1 by 2 is gamma 1 by 2 times gamma 1 by 2 by gamma 1 by 2 plus 1 by 2. It's going to be root pi times root pi by gamma 1, right? Gamma 1 going to be 0 factorial, it's going to be pi. Now this PDF I can write 1 by pi 1 plus t square whole to the power of minus 1. I can write 1 by 1 plus t square. So for n equal to 1, the PDF of t at t going to be 1 by pi times 1 plus t square for minus infinity less than t less than infinity. Okay, you can see that this is the PDF of Cauchy distribution. So for n equal to 1, this t actually follows Cauchy distribution. So Cauchy distribution going to be special case of the t distribution. Okay, so t distribution with a 1 degree of freedom actually Cauchy distribution. We already know for a Cauchy distribution expectation do not exist. Fine. Okay, so for n equal to 1, the expectation of t do not exist. Okay. Now for n greater than or equal to, if you want to see expectation of t, what is t? T x by root y by n. Okay, so you can think like this one, g of x times h of y, where g of x is h of y is 1 by under root y by n. Since x and y are independent, so expectation of g of x times h of y should be equal to expectation of g of x times expectation of h of y when x and y are independent. So this expectation of x by root y by n, I can write expectation of x times expectation of 1 by root y by n. Okay, and here x is a standard normal random variable. Okay, so expectation of x going to be 0. So that 0 times something is going to be 0. For n greater than or equal to, expectation of t going to be 0. Okay, fine. Now variance of t is actually what? Expectation t square minus expectation t whole square, but expectation t 0, so that's why the variance of t simply going to be expectation of t square. Now t equal to x by root y by n, so the t square going to be x square by y by n. Okay, so expectation t square going to be expectation of x square by y by n. Okay, now this x square by y by n I can write as x square times n by y. It look like a g of x times h of y. Okay, since x and y are independent, we should have expectation of g of x times h of y same as expectation of g of x times expectation of h of y. So this expectation of x square by y by n, I can write expectation x square times expectation of n by y, and here x is a standard normal random variable. Okay, so expectation x square going to be variance of x plus expectation of x whole square. Okay, variance of x is 1 and expectation x is 0, so 1 plus 0 square going to be 1. That's why this expectation x square going to be 1. Now this expectation of n by y, I can write n times expectation of 1 by y. Okay, now this expectation of 1 by y going to be 1 by n minus 2. Okay, so expectation of 1 by y, what do you do? Y is a chi-square random variable with a n degrees of freedom. So expectation of 1 by y going to be integral 0 to infinity 1 by y. So this is a PDF of chi-square random variable with n degrees of freedom. Now this 1 by y to the power of n by 2 minus 1, I can write y to the power of n minus 2 by 2 minus 1. Okay, now this 2 to the power of n by 2, I can write 2 times 2 to the power of n minus 2 by 2. So this 2 to the power of n by 2, I am writing 2 to the power of n minus 2 by 2 times 2. Okay, and this n by 2, I can write n minus 2 by 2 plus 1. We know that gamma alpha plus 1 going to be alpha times gamma alpha. So that's why the gamma n by 2, I can write gamma n minus 2 by 2 plus 1. This I can write n minus 2 by 2 times gamma n minus 2 by 2. Okay, that's why here this gamma n by 2, I'm writing n minus 2 by 2 times gamma n minus 2 by 2. Fine. Okay, now again this look like a PDF of chi-square distribution with n minus 2 degrees of freedom. So this integral value must be equal to 1. Okay, so here 2 to cancel, so we have 1 by n minus 2 times this integral value 1. That's why this expectation of 1 by y equal to 1 by n minus 2. Okay, so we have n by n minus 2. This is the variance of t. Okay, variance of t distribution with n degrees of freedom equal to n by n minus 2. Fine. Here is the sketch for the PDF of t distribution with a 1 degree of freedom, 2 degrees of freedom, 3 degrees of freedom, 5 degree of freedom, 9 degree of freedom. Fine. Now the CDF of t, which follows the t distribution with n degree of freedom, the CDF of t at x in terms of the PDF of t going to be this: integral minus infinity to x small ft of t dt. Okay, here this is the PDF of t at t. Okay, this integral is not going to be easy one to get the closed form expression. That's why to get these CDF values, one has to use some software packages. Okay, here is an application using which you can get these CDF values for various degrees of freedom and various values of x. Let me show you. Okay, let me set n value, let's say 6, and x value 0.98. Okay, now the CDF value of t distribution with 6 degree of freedom at 0.98 value is 0.8175, which is the area under the PDF of t distribution with 6 degree of freedom from minus infinity to 0.98. This is the region under the PDF curve that is left to the 0.98 location. Okay, fine. Now you can play with this to get the CDF values for t distribution with a various degrees of freedom. Okay, fine. For 0 less than alpha less than 1, a real number x such that probability of tn greater than x equal to alpha is denoted by t alpha n. This t alpha n is the location on the real line for which area under the PDF of tn right side of this location equal to exactly alpha. Such a location is denoted by T alpha n. These T alpha n values are heavily used in many statistical methods To get these T alpha n values, one has to either use some software packages or refer to some T distribution tables which can be found in many statistics books. Okay, here is an application using which you can get this T alpha n values for various values of n and alpha. Okay, let me show you. So let me set n value 7, alpha value 0.05. See, now let's see what is the T alpha n value for alpha equal to 0.05 and n equal to 7 degrees of freedom. So what we got here, 1.895. Okay, this is the PDF of T distribution with 7 degrees of freedom. So this red dot is the location 1.895. Okay, now the area of this yellow shaded region, which is the area under the T7 PDF curve right side of this red dot, is exactly equal to 0.05. Okay, likewise you can get the T alpha n values for various values of alpha and n. I hope you can play with this. Now if this is the T alpha n, then for minus T alpha n location, because of symmetry, as this area equal to alpha, this area also must be equal to alpha because of symmetry. Okay, so area under this PDF curve, left side of this minus T alpha n equal to alpha. So what should be the area under this PDF curve, right side of this minus T alpha n? This area must be equal to 1 minus alpha. So it's clear that T1 minus alpha comma n value same as minus T alpha n value. Okay, so let me show you that. By symmetry we can see that the probability of Tn less than or equal to minus T alpha n also alpha. That's what I showed. If this is a minus T alpha n, the area that is covered left side of this minus T alpha n also going to be same alpha. Okay, this is clear from symmetry. Okay, now the probability of Tn less than or equal to minus T alpha n, I can write 1 minus probability of Tn greater than minus T alpha n. So this I can write probability of Tn greater than minus T alpha n equal to 1 minus alpha. Okay, so this is a number, let's say x, such that the probability of Tn greater than x equal to 1 minus alpha. So this x is denoted by what? T1 minus alpha comma n. So what is this T1 minus alpha comma n? Actually minus T alpha n. Okay, so that's why we have minus T alpha n equal to T1 minus alpha comma n. Okay, fine. This is the table that you can find in many statistics book. Here we have this T alpha n values for some standard values of alpha. Alpha equal to 0.1, alpha equal to 0.05, alpha equal to 0.025, alpha equal to 0.01, and alpha equal to 0.005. These are some standard values of alpha for which we use this T alpha n values in practice, and we have up to 30 degrees of freedom. We have this T alpha n values for up to 30 degrees of freedom. Okay, fine. Now we are going to see F distribution. Let x and y are independent random variables. Here x is a chi-square random variable with n degrees of freedom. Y is a chi-square random variable with m degrees of freedom. Then u equal to x by n by y by m. You can also write like mx by ny is said to have F distribution on n and m degrees of freedom. Here order matters. Okay. Now we want to see the PDF of u. Here u look like a g of xy. We know the technique to find out the PDF of u. What you do? You introduce another auxiliary transformation like v equal to y. Then you find out the joint PDF of uv in terms of the joint PDF of xy and the Jacobian of the transformation. Then you can find out the PDF of u as a marginal PDF, simply integrating joint PDF of uv with respect to v, okay, from minus infinity to infinity. This is how we are going to get the PDF of u. First, we need a joint PDF of x. What do we know here? X is a chi-square random variable with a n degrees of freedom. So I can write the PDF of x, fx of x equal to 1 by 2 power n by 2 gamma n by 2 times x to the power of n by 2 minus 1 times e power minus x by 2 for x positive, 0 otherwise. Okay, and y is the chi-square random variable with m degrees of freedom. So the PDF of y, fi of y equal to 1 by 2 to the power of m by 2 gamma m by 2 times y to the power of m by 2 minus 1 times e power minus y by 2 for y positive, 0 otherwise. Okay. Here x and y are independent random variables. So the joint PDF of xy we can write product of marginal PDF. So the joint PDF of xy is going to be PDF of x times PDF of y. Okay, now if I multiply these two PDFs, so we get the joint PDF of xy like this. 1 by 2 to the power of n by 2 times 2 to the power of n by 2 I can write 2 to the power of n plus m by 2 gamma n by 2 times gamma m by 2, okay, times x to the power of n by 2 minus 1 times y to the power of m by 2 minus 1 and e power minus x by 2 times e power minus y by 2 I can write e power minus of x plus y by 2 for x positive, y positive, 0 otherwise. Okay, this is the joint PDF of xy. Okay, so this is the joint PDF of xy. Okay, now let us consider the transformation u equal to mx by ny and auxiliary transformation v equal to y. Okay, then these transformations u equal to mx by ny, v equal to y can be uniquely solved for x and y like this. X equal to nuv by m, y equal to v. Then the Jacobian of this transformation going to be determinant of this 2 by 2 matrix. Here dou x by dou u going to be nv by m, dou x by dou v going to be nu by m, that you can see from this. Dou y by dou u going to be 0, dou y by dou v going to be 1, that you can see from this. And determinant of this 2 by 2 matrix going to be nv by m. Okay, so this is the Jacobian of the transformation. Fine. Now the joint PDF of uv in terms of joint PDF of xy and the Jacobian of this transformation is this. Okay, fu of uv at u comma v is fxy of nuv by m comma v times modulus of the Jacobian that we got nv by m. Fine. Okay, now what is the joint PDF of xy that we got? 1 by 2 to the power of n plus m by 2 gamma n by 2 times gamma m by 2 x to the power of n by 2 minus 1 y to the power of m by 2 minus 1 e power minus of x plus y by 2. This is for x positive and y positive. Okay, now to see this, we simply substitute nuv by m for x, v for y in the joint PDF of xy. So we will have this 1 by 2 to the power of n plus m by 2 gamma n by 2 gamma n by 2 times nuv by m all to the power of n by 2 minus 1 v to the power of m by 2 minus 1 e power minus of nuv by m plus v by 2 times modulus of nv by m. Okay, this is the modulus of the Jacobian. Jacobian is nv by m. Fine. Now this gets simplified to here anyway v positive. So I don't have to put modulus here. I can simply write n by m v. Now here is n by m all to the power of n by 2 minus 1 times n by m. So I can write n by m all to the power of n by 2. Here I got a u to the power of n by 2 minus 1. Okay, and here v to the power of n by 2 minus 1 times v to the power of n by 2 minus 1 times v. I can write v to the power of n plus m by 2 minus 1. Okay, now here e to the power of, here I can take v common, so I can write e power minus v by 2 of nu by m plus 1 by 2 to the power of n plus m by 2 gamma n by 2 times gamma m by 2. Okay, fine. Okay, so this is the joint PDF of UV for U positive and V positive. Fine. Now we are going to see the PDF of U as a marginal PDF. So to get the PDF of U, we integrate the joint PDF of UV with respect to V from minus infinity to infinity. But here V positive, so it's enough to integrate from 0 to infinity. Okay, let's integrate joint PDF of UV with respect to V from 0 to infinity. So this is what we will have. Here, things not involving V, I am writing out of the integration. So these are the things not involving V. Okay, now we end up integrating only this. Okay, now here we are going to take a substitution for this. Let me take t equal to v by 2 of nu by m plus 1. That implies dt going to be equal to 1 by 2 of nu by m plus 1 dv. Okay, from this I can write v equal to 2t by nu by m plus 1. Okay, from this I can also write dv equal to 2 dt by nu by m plus 1, and with this relation the t limits are also going to be from 0 to infinity. Okay, so now this integral I can write down like this. Okay, so integral 0 to infinity, this v I can replace with this one. So we have a 2t by nu by m plus 1 all to the power of n plus m by 2 minus 1, and this got replaced by t, so we have e power minus t, and this dv got replaced by this one 2 dt by nu by m plus 1. So this is a 2 dt by nu by m plus 1. Okay, now here we have a 2 to the power of n plus m by 2 minus 1, and here we got a 2. So this whole thing get cancelled with this one. Okay, now here in the denominator we have a nu by m plus 1 all to the power of n plus m by 2 minus 1. Here in the denominator we have nu by m plus 1. The total is nu by m plus 1 all to the power of n plus m by 2 in the denominator, that we can write out of this integration like this. Okay, first let me write n by m all to the power of n by 2 u to the power of n by 2 minus 1 by gamma n by 2 gamma m by 2. Then we have nu by m plus 1 all to the power of n plus m by 2. Then we have integral 0 to infinity. Okay, t to the power of n plus m by 2 minus 1. Okay, times e power minus t dt. Okay, fine. This is what we ended up with. Okay, so now this can be seen as gamma integral. It's going to be gamma n by 2 plus m by 2. Okay, so let me write down. Now this gamma n by 2 plus m by 2, if I write here, okay, this will turn out to be beta function at n by 2 comma m by 2, beta of n by 2 comma m by 2. So our PDF is going to be this. So this is our PDF of u. F u of u equal to n by m all to the power of n by 2 times u to the power of n by 2 minus 1 by beta of n by 2 comma m by 2 times nu by m plus 1 all to the power of n plus m by 2 for u positive, 0 for u less than or equal 0. This is a PDF of u which follows the f distribution with n and m degrees of freedom. Okay. Now let me show you the sketches of the PDF of f distribution for various values of n and m. Okay. This is for n equal to 1, m equal to 1. This is for n equal to 2, m equal to 1. This is for n equal to 5, m equal to 2. This is for n equal to 10, m equal to 1. This is for n equal to 50 and m equal to 50. Fine? Okay. Now, the CDF of u at x going to be integral minus infinity to x small fu of t dt, where the small fu is PDF of u. Okay, since u is a positive random variable, so it's enough to integrate from 0 to x. So for x positive, and this is the PDF of u at t. So this integral value going to be area under the PDF curve from 0 to x. For example, if this location is x, then area of this green shaded region going to be capital Fu of x. Okay, this is the CDF value of u at x. Fine, but this integration is not going to be easy one to write this CDF of u in closed form. That's why to get these CDF values, one has to use some software packages. Here is an application using which you can get these CDF values for various values of n and m. Okay, let me show you. Okay, now let me change n value to 5, m value to 7, x value to 1.29. See, so we have a CDF value of u at 1.29 is 0.6344. Okay, this location is 1.29. So area of this green shaded region is going to be fu of 1.29, which equal to 0.6344. Okay, so this is how you can get the CDF values of f distribution for various values of n and m. Okay, feel free to play with this. Okay, this is the notation. We read it as u follows the f distribution with n and m degrees of freedom. Okay, fine. Now let us see expectation of u. Okay, here u is what? Mx by ny, where x is a chi-square random variable with n degrees of freedom, y is a chi-square random variable with m degrees of freedom, and this x and y are independent. Okay, now so expectation of u, what is u here? Mx by ny. So this expectation of mx by ny, I can write m by n times expectation of x by y. This x by y I can see as x times 1 by y. You can think like a g of x times h of y. Since x and y are independent, so expectation of g of x h of y must be same as expectation of g of x times expectation of h of y. That's why this expectation of x by y I can write expectation of x times expectation of 1 by y. Since x is a chi-square random variable with n degrees of freedom, so expectation of x going to be equal to n. Okay. Now y is a chi-square random variable with m degrees of freedom. So this expectation of 1 by y is going to be 1 by m minus 2, because we already worked with this calculation. So expectation of 1 by y will be 1 by m minus 2. Okay, now this n cancel. Okay, so we'll end up with m by m minus 2. So expectation of f distribution with n and m degrees of freedom equal to m by m minus 2. Fine. Okay, now let us look at the variance of u. For that we need a expectation u square first, so that we can write variance of u as expectation of u square minus expectation of u whole square. We already got this expectation u. All we need is expectation u square. Okay, first of all let us look at expectation u square. Now the expectation of u square, first of all, u equal to mx by ny, that implies u square equal to m square x square by n square y square. Okay, so that's why expectation of u square equal to expectation of m square x square by n square y square. This we can write m square by n square times expectation of x square by y square. Again, this x square by y square we can see as x square times 1 by y square. Again, you can think like a g of x times h of y. Since x and y are independent, expectation of g of x h of y must be same as expectation of g of x times expectation of h of y. That's why this expectation of x square by y square we can write expectation x square times expectation 1 by y square. Okay. Now here x is a chi-square random variable with the n degrees of freedom. So expectation x is n and the variance of x is 2n. So what will be expectation x square? It will be variance of x plus expectation x whole square. It's going to be 2n plus n square. Okay. So this expectation x square I am writing as 2n plus n square. Now y follows the chi-square distribution with m degrees of freedom. So I can calculate this expectation 1 by y square just like the way I calculated expectation 1 by y. Feel free to verify this. You will end up with 1 by m minus 2 m minus 4. So that's why this expectation 1 by y square going to be 1 by m minus 2 m minus 4. Okay, this whole thing gets simplified to this m square times 2 plus n by n times m minus 2 times m minus 4. This is the expectation of u square. Now we are in a position to calculate variance of u. Now the variance of u going to be expectation u square minus expectation u whole square. We already got expectation u as m by m minus 2. So now expectation u square we just got. Okay, this one m square times 2 plus n by n times m minus 2 times m minus 4 and expectation u m by m minus 2. So expectation u whole square going to be m square by m minus 2 whole square. Okay, so this is what expectation u whole square. This whole thing gets simplified to this one. Okay, 2m square times m plus n minus 2 by n times m minus 2 whole square times m minus 4. So this is the variance of u, where u follows f distribution with n and m degrees of freedom. Okay, fine. For 0 less than alpha less than 1, a real number x such that probability of f and m greater than x equal to alpha is denoted by f alpha n m. This x is the location on the real line for which area right to this location under the PDF of f and m exactly equal to alpha. Such a location is denoted by f alpha n m. Okay, these values are used in many statistical methods. To get these values, one has to use software or refer to f distribution table, which can be found in statistics books. Here is an application using which you can get these f alpha n m values. Let me show you. Okay, here let me change into 5, m to 7, okay, some alpha something 0.05. Okay, now you see this red dot is the location which is actually 3.972 that you can see from here. Okay, so area right to this location under the PDF of f distribution with the n equal to 5, m equal to 7 degrees of freedom equal to exactly 0.05. Okay, okay. Now you can play with this to get the f alpha nm values for different values of n, m, and alpha. Okay, fine. Note 1 by f alpha nm equal to f1 minus alpha mn. Please note the order here. Here we have a mn, here we have a nm. Okay, fine. We know what is the meaning of f alpha nm. F alpha nm is the real number for which the probability of fnm greater than f alpha nm equal to alpha. Okay. Now this fnm is a random variable which follows the f distribution with n and m degrees of freedom. So this fnm I can express like mx by ny, where x is the chi-square random variable with n degrees of freedom, y the chi-square random variable with m degrees of freedom. Of course, they are independent. Then this f and m I can write as mx by ny because this follows f distribution with n and m degrees of freedom. Okay, fine. Now mx by ny greater than f alpha nm if and only if 1 by mx by ny less than 1 by f alpha nm. This one I can write ny by mx. Okay. Now I can write the probability of ny by mx less than 1 by f alpha nm equal to alpha, because this is true if and only if this is true. So whenever this happens, this happens. That's why the probability of this event must be same as probability of this event. That's why I can write probability of ny by mx less than 1 by f alpha nm equal to alpha. Okay, fine. Now this ny by mx we can see as y by m by x by n. So this is going to follow f distribution with m and n degrees of freedom. So that's why now I can write this one as probability of fmn less than 1 by f alpha nm equal to alpha. Fine. Okay. Now this probability I can write 1 minus probability of fmn greater than or equal to 1 by f alpha nm equal to alpha. From this I can write probability of fmn greater than or equal to 1 by f alpha nm equal to 1 minus alpha. If you think this is like x, for this x, we have probability of fmn greater than or equal to x equal to 1 minus alpha. So what should be this x? This must be equal to f1 minus alpha mn. But what is this actually? 1 by f alpha nm. This is the relation. Fine. Okay. Note 2. If x follows the t distribution with m degrees of freedom, then x square follows the f distribution with 1 and m degrees of freedom. Okay, the proof is easy. Here is the proof. First of all, x can be expressed like this: z by under root chi square m by m. Here z is a standard normal random variable. Then x square going to be z square by chi square by m. Here z square follows the chi square distribution with 1 degree of freedom. That's why this z square I can write chi square 1 by 1. So we have now chi square 1 by 1 by chi square m by m. So which follows the f distribution with 1 and m degrees of freedom. Fine. Now we are going to look at some sampling distributions. Before that, let me introduce some terminology. Okay. Population. A population is a collection of measurements. For example, a population may consisting of heights of the students in a particular college, or a population may consisting of salaries of an employees in particular organization. Okay. A population may follow some probability distribution. For example, heights of a students in your college may follow some normal distribution with some mean parameter mu and some variance parameter sigma square. Okay, fine. A sample. A subset of a population is called sample. Next, we are going to talk about random sample. Random sample means intuitively a random subset of a population. Okay. The mathematical definition is the following. First of all, let us say our population is with a CD of capital Fx. A collection of n IID random variables with a CD of capital Fx is called random sample of size n from the population with a CD of capital Fx. This is the mathematical definition for random sample. Let me make sense out of this definition. Let us say you are selecting n heights at random from the population consisting of heights. The first height observation that you got, let us denote by capital X1. Second height observation that you got, let us denote by capital X2, so on. Nth height observation that you got, let us denote by capital Xn. Okay. If you really select these n height observation at random, then these X1, X2, Xn going to be independent random variables. Okay. They are going to be independent. Okay. Since all observation come from the population having the CD of capital Fx, so all xi's having the same CD of capital Fx. That's why these x1, x2, xn are going to be IID random variables, okay, having the CD of capital Fx. Okay, that's why this collection of n IID random variables having the CD of capital Fx is called random sample of size n that come from the population having the CD of capital Fx. Fine. Next, statistic. Any function of the random sample is called statistic. If x1, x2, xn is some random sample of size n that come from some population, then a function of x1, x2, xn is called statistic for that population. Okay, let me give some examples for these statistics. If we let x1, x2, so on, xn be random sample of size n that come from some population, then the sample mean, which is denoted by x bar. If you want to emphasize size of the sample, you can also write xn bar. Okay, so this x bar is 1 by n summation I equal to 1 to n xi, which is a function of random sample x1, x2, xn. So this is the one example of a statistics. Okay. Another example is sample variance, which is denoted by s square. Okay. So which is 1 by n minus 1 of summation I equal to 1 to n xi minus x bar whole square. Here x bar is the sample mean. So the whole thing is going to be function of x1, x2, xn. So the sample variance is another example of a statistics for the population. Okay. Next, sample median. If n is odd, the middle order statistics is called sample median. If n is even, the average of two middle order statistics is called sample median. Okay. We know these order statistics are functions of x1, x2, xn. So the sample median going to be function of x1, x2, xn. So the sample median is the example of a statistics. Okay. Next example, sample range. Highest order statistics minus lowest order statistics, that is x bracket n minus x bracket 1 is called sample range. Each one is function of x1, x2, xn. So the whole thing is going to be function of x1, x2, xn. So this is an example of a statistics for the population. Okay, fine. Theorem. Let x1, x2, so on, xn are IID normal random variables with a mean mu and variance sigma square. Then root n of x bar minus mu by sigma follows the standard normal distribution, and the root n of x bar minus mu by s follows the t distribution with n minus 1 degrees of freedom. Okay, first let me show you this. Okay, first of all, we know that any linear combination of normal random variables, again normal random variables. So this x bar will be normal for sure. The question is, what is the mean parameter and what is the variance parameter. Let's find out expectation x bar and the variance of x bar. Expectation x bar, we know that expectation of the linear combination going to be linear combination of expectation. Okay, so because of the linear property, so this expectation of 1 by n summation I equal to 1 to n xi, I can write 1 by n of summation I equal to 1 to n expectation xi, and expectation xi going to be mu for I equal to 1 to n. So we have 1 by n times n mu, n cancel, we have a mu. So this expectation x bar equal to mu. Okay, now let us look at the variance of x bar. Now the variance of x bar, what is x bar? 1 by n summation I equal to 1 to n xi. We know that the variance of ax we can write a square times variance of x. So first I can write this one 1 by n square times variance of summation I equal to 1 to n xi. Again here x1, x2, xn are independent. So the variance of the summation xi going to be sum of this variance of xi from I equal to 1 to n. Okay. Now 1 by n square times summation I equal to 1 to n variance of xi, and each variance of xi equal to sigma square. Now we have 1 by n square times n sigma square. This n square will go, we have sigma square by n. So the variance of x bar equal to sigma square by n. So here x bar is the normal random variable with the mean parameter mu and the variance parameter sigma square by n. Okay, so what will be the standard deviation? It's going to be sigma by root n. Okay, now so we can say that this x bar follows the normal distribution with the mean parameter mu, variance parameter sigma square by n. So we can say that this x bar minus mu by sigma by root n follows the standard normal distribution. This we can write root n of x bar minus mu by sigma. Okay, fine. Next I am going to show that this root n of x bar minus mu by s follows the t distribution with n minus 1 degrees of freedom. Okay, fine. Now let me consider the summation. Summation I equal to 1 to n xi minus mu whole square. Here let me subtract x bar and add x bar. Okay. Now you can think like this is a, this is b. In each term expand like a plus b whole square. Then in each term you will have this xi minus x bar whole square plus x bar minus mu whole square plus 2 times xi minus x bar times x bar minus mu. Fine. If you take the summation inside, I can write like this. Summation I equal to 1 to n xi minus x bar whole square plus summation I equal to 1 to n x bar minus mu whole square. This you can write n times x bar minus mu whole square plus here this 2 times x bar minus mu common to each term in the summation. So I can write this 2 times x bar minus mu of summation I equal to 1 to n xi minus x bar. Okay. Next we are going to realize that this sum is going to be 0 because the summation I equal to 1 to n xi minus x bar, I can write the summation I equal to 1 to n xi minus nx bar, and we know that x bar is what? 1 by n summation I equal to 1 to n xi. So that implies the summation xi from I equal to 1 to n, I can write nx bar. So we have nx bar minus nx bar, that is 0. So that's why this sum is going to be 0. Now we end up with only this part. Okay, fine. Summation I equal to 1 to n xi minus x bar whole square. Now here also I can write like this, root n of x bar minus mu whole square. Okay, so fine. So we have this. So we have the summation I equal to 1 to n xi minus mu whole square equal to summation I equal to 1 to n xi minus x bar whole square plus root n of x bar minus mu whole square. Now let me divide each side by sigma square. Okay, let me rewrite like this. summation I equal to 1 to n xi minus mu by sigma whole square equal to summation I equal to 1 to n xi minus x bar by sigma whole square plus root n of x bar minus mu by sigma whole square. Okay, we know that this xi follows the normal distribution with a mean parameter mu and variance parameter sigma square for I equal to 1 to so on n. That implies this xi minus mu by sigma follows the standard normal distribution. Let me call it zi. Okay, then this zi square will follow the chi-square distribution with 1 degree of freedom for I equal to 1 to so on n. Since here x1, x2, xn are independent, that implies this z1, z2, zn also independent. That implies this z1 square, z2 square, zn square also independent. So each one here follows the chi-square distribution with 1 degree of freedom. So this one you can see as sum of n independent chi-square random variable with a 1 degree of freedom. So this whole sum is going to follow chi-square distribution with n degree of freedom. Fine. And also we know that this root n of x bar minus mu by sigma follows the standard normal distribution that we already seen. So if you call it z, then this z square follows the chi-square distribution with 1 degree of freedom. So this one follows the chi-square distribution with 1 degree of freedom. Here the right hand side, this one follows the chi-square distribution with 1 degrees of freedom. So this one must follow the chi-square distribution with n minus 1 degrees of freedom, so that this sum will follow chi-square distribution with n degrees of freedom. So we have this summation I equal to 1 to n xi minus x bar by sigma whole square follows the chi-square distribution with n minus 1 degrees of freedom. Okay. Now if I write this sigma in the denominator outside, then I can write 1 by sigma square summation I equal to 1 to n xi minus x bar whole square. Okay. Now if I multiply and divide by n minus 1, I can write like this. Okay. Okay. Now what we have here, n minus 1. Here this one is going to be s square, sample variance s square by sigma square follows the chi-square distribution with n minus 1 degrees of freedom. So we have this. Okay. So this summation I equal to 1 to n xi minus x bar by sigma whole square, same as this n minus 1 s square by sigma square, which follows the chi-square distribution with n minus 1 degrees of freedom. Fine. Okay. Now let me consider root n of x bar minus mu by s. Okay. Now let me divide numerator and denominator by sigma. Okay. Now let me write this denominator as under root s square by sigma square. Also let me multiply and divide by n minus 1. Okay, like this. Okay, fine. Here you can see that now we already know this root n of x bar minus mu by sigma follows the standard normal distribution. You can think like this one is z. Okay. Now we already know that this n minus 1 s square by sigma square follows the chi-square distribution with n minus 1 degrees of freedom. And one more thing, this x bar minus mu and s square are going to be independent. I will show that after this one. So now this one look like z by under root chi-square n minus 1 by n minus 1. So this exactly follow t distribution with n minus 1 degrees of freedom. Fine. Okay. Okay. So therefore, this root n of x bar minus mu by s follows the t distribution with n minus 1 degrees of freedom. Okay. Now let me show this x bar minus mu and s square are independent when this x1, x2, so on, xn are IAD normal random variable with a mean mu and variance sigma square. Okay. X bar minus mu and s square are independent when x1, x2, so on, xn are IID normal random variable with a mean mu and variance sigma square. First, what I will do, I will show this x bar and xi minus x bar are independent for all I equal to 1 to n. Then I will show this x bar minus mu s square are independent. Fine. Okay, proof. First we know x bar equal to 1 by n summation j equal to 1 to n xj, s square equal to 1 by n minus 1 half summation j equal to 1 to n xj minus x bar whole square. We also know that this x bar follows the normal distribution with a mean parameter mu and variance parameter sigma square by n, as this x1, x2, xn are IID normal random variable with a mean mu and variance sigma square. Okay, now x bar is normal, xi's are normal, so we can say xi minus x bar will be again normal, because linear combination of normal random variables again normal random variable. Fine. Now x bar is normal, xi minus x bar is normal, so the joint distribution of x bar and xi minus x bar will be bivariate normal distribution. So we can say that the joint distribution of x bar and xi minus x bar will be bivariate normal distribution for all I equal to 1 to n. And we know that when xy follows the bivariate normal distribution, the covariance of xy equal to 0 implies x and y are independent, right? So we can say that covariance of x bar comma xi minus x bar equal to 0 implies x bar and xi minus x bar are independent for all I equal to 1 to n. So now I'll try and show the covariance of x bar comma xi minus x bar equal to 0 for all I. Okay. Now let me look at covariance of x bar comma xi minus x bar. Covariance of x bar comma xi minus x bar. First I can write this one, covariance of x bar comma xi minus covariance of x bar comma x bar using the covariance property. Now this one, if you replace x bar with a 1 by summation j equal to 1 to n xj, now we have this. Now covariance of x bar comma x bar here. Now again using the covariance property, this one we can write 1 by n out, then 1 by n of summation j equal to 1 to n covariance of xj comma xi, and the covariance of x bar comma x bar will be variance of x bar. Now in this summation, the covariance of xj comma xi will be either equal to 0 or sigma square. It will be 0 when I not equal to j and equal to sigma square when I equal to j. That means in this summation only one term will be equal to sigma square, everything else will be 0. So the whole sum will be equal to sigma square. So here you will have 1 by n times sigma square, and variance of x bar will be what? Sigma square by n. So here we have a sigma square by n. So now sigma square by n minus sigma square by n. So we got 0. So covariance of x bar comma xi minus x bar equal to 0. So we can say x bar is independent of xi minus x bar for all I equal to 1 to n. So x bar should be independent of any function of this xi minus x bar. So in particular, x bar will be independent of summation I equal to 1 to n xi minus x bar whole square. So we can say that x bar and s square are independent, because what is s square? S square equal to this 1 by n minus 1 half summation j equal to 1 to n xj minus x bar whole square. So we can say x bar minus mu and s square also independent, because x bar comma s square are independent means simply x bar minus mu s square also should be independent. Fine. Okay. Note that x1, x2, so on, xn are IID normal random variables with a mean parameter mu x and the variance parameter sigma x square, and y1, y2, ym are IID normal random variables with a mean parameter mu y and the variance parameter sigma y square. That is, this is a random sample of size n that come from the population having the normal distribution with the mean parameter mu x and the variance parameter sigma x square. This is another random sample of size m that come from the population having the normal distribution with the mean parameter mu y and the variance parameter sigma y square. Okay, so this sx square is the sample variance of this random sample, and sy square is the sample variance of this random sample. Then the sigma y square sx square by sigma x square sy square follows the f distribution with n minus 1 and m minus 1 degrees of freedom. Okay, it's easy. Let me prove this. Here the sigma y square sx square by sigma x square sy square, I can write like this: sx square by sigma x square by sy square by sigma y square. Okay, now here let me multiply divide by n minus 1 in the numerator. Okay, let me multiply and divide by m minus 1 in the denominator. Okay, now this part follows the chi-square distribution with n minus 1 degrees of freedom. This part will follow the chi-square distribution with m minus 1 degrees of freedom. So I can write pi square n minus 1 by n minus 1 by chi square m minus 1 by m minus 1. So this exactly follows f distribution with n minus 1 and m minus 1 degrees of freedom. Okay, so this is the proof. Okay, example: suppose scores on IQ test are normally distributed with a population mean 100, and suppose 20 people are randomly selected and tested. The standard deviation in the sample group is 15. That is, sample standard deviation is 15. What is the probability that average test score in the sample group will be at most 110? Okay, fine. Here, let x1, x2, so on x20 represent score of 20 people. This is a random sample of size 20. Here n equal to 20. Okay. Here what we know the population mean mu, and we don't know the population variance. Okay. Okay. Fine. Here x bar is the sample mean of random sample of size 20. So x bar equal to 1 by 20 of summation I equal to 1 to 20 xi, and the sample standard deviation, the smallest value 15. Okay, and the population mean mu equal to 100. Okay, here we are interested in the probability of x bar less than or equal to 110. Here, we know that x bar follows the normal distribution with a mean parameter mu and the variance parameter sigma square by n, that is 20. But we don't know the sigma square here. Okay, here we don't know the population variant, so we cannot use this fact here. Okay, so but what we know here, sample standard deviation. So if I consider the random variable t, which is a root 20 of x bar minus 100 by 15, this look like a root n of x bar minus mu by s, which follows the t distribution with n minus 1 degrees of freedom. Here n equal to what? 20. So this t will follow t distribution with 19 degrees of freedom. Okay. So to answer this question, I'm going to use t distribution with 19 degrees of freedom. Okay. Now, here we are interested in the probability of x bar less than or equal to 110. Now this event x bar less than or equal to 110, I can write like this. Okay. If I subtract mean 100 each side, okay, then we can multiply root 20 each side. Then we can divide sample standard deviation 15 each side. Okay, so this event happen if and only if this event happens. So the probability of x bar less than or equal to 110 is going to be same as the probability of this event. Okay, now we know this follows the t distribution with 19 degrees of freedom, and this gets simplified to 2.981. Okay, so this is the random variable t which follows the t distribution with 19 degrees of freedom. So we have this probability of t less than or equal to 2.981, and this probability going to be CDF value of t distribution with 19 degrees of freedom at 2.981. Okay, this CDF value will be 0.9961611. Okay, we can get it from starts module in the scipy package. Okay, we imported starts module from the scipy package, then we created t random variable with 19 degrees of freedom, then we are calling CDF method at 2.981, which should return the CDF value of t distribution with 19 degrees of freedom at 2.981. Let me show you. So this is the CDF value of t distribution with a 19 degrees of freedom at 2.981. Okay, fine. Next example, the time it takes a CPU unit to process certain types of job is normally distributed with a mean 20 seconds and standard deviation 3 seconds. Here the population mean 20 seconds and the population standard deviation sigma equal to 3 seconds. If a sample of 15 jobs is observed, what is the probability that sample variance will exceed 12? Okay, here the sample size n equal to 15 and the population variance sigma square equal to 9, because population standard deviation sigma equal to 3, so sigma square going to be 9. Okay, now let me consider the random variable x, which is a 14 s square by 9. This look like n minus 1 s square by sigma square for n equal to 15, sigma square equal to 9. Okay, we know that this n minus 1 s square by sigma square follows the chi-square distribution with n minus 1 degrees of freedom. So I can say that this 14 s square by 9 will follow chi-square distribution with 14 degrees of freedom. So this x follows the chi-square distribution with 14 degrees of freedom. Here we are interested in the probability of s square greater than 12. Okay, now so this event s square greater than 12 will be equivalent to, if I multiply 14 each side and if I divide by 9 each side, okay, so this event equivalent to this event, so the probability of this event will be same as probability of this event. Okay, now so the probability of s square greater than 12 equal to probability of 14 s square by 9 greater than 14 times 12 by 9. Okay, and this one we call x, which follows the chi-square distribution with 14 degrees of freedom, and this gets simplified to 18.67. So we have this probability of x greater than 18.67. This we can write 1 minus probability of x less than or equal to 18.67. Here this x follows the chi-square distribution with 14 degrees of freedom. So this probability of x less than or equal to 18.67, I can write CDF value of chi-square distribution with a 14 degrees of freedom at 18.67. Okay, this value will be equal to 0.8221. So this 1 minus 0.8221 value will be 0.1779. Okay, to get this CDF value, we can use this scipy package. Okay, so we can import start from scipy package and you can create this chi-square random variable with a 14 degrees of freedom. Then you can call the CDF method at 18.67. Okay, let me show you the value here. So this is the CDF value of chi-square distribution with a 14 degrees of freedom at 18.67. Okay, fine. In this solution, we didn't use given population mean. Next example, in a particular college, girls' weights are normally distributed with a mean 50 kg and standard deviation 6 kg, and boys' weights are normally distributed with a mean 60 kg and standard deviation 5 kg. If we select 10 girls at random, which makes group 1, and 12 boys at random, which makes group 2, find the probability that sample standard deviation of group 1 less than the sample standard deviation of group 2. Here we have two populations, one population consisting of girls' weights, another population consisting of boys' weights. Okay, from one population, we are getting random sample of size 10, which represent group 1. From another population, we are getting random sample of size 12, which represent group 2. Okay, fine. Here, let x1, x2, so on, xn be the random sample representing group 1, and y1, y2, so on, ym be the random sample representing group 2. So here, the sample size n equal to 10, and the population mean mu x equal to 50 kg, and the population variance sigma x square going to be 36 because population standard deviation 6 kg, so it will be 36. And here the sample size m equal to 12, and the population mean mu y equal to 60 kg, and the population variance sigma y square going to be 25 because population standard deviation 5 kg, so it will be 25. Okay, so here we have n equal to 10, mu x equal to 50, sigma x square equal to 36, m equal to 12, mu y equal to 60, sigma y square equal to 25. Okay, fine. We know that this sigma y square sx square by sigma x square sy square follows the f distribution with n minus 1 and m minus 1 degrees of freedom. Here sx square denotes the sample variance of group 1, sy square denotes the sample variance of group 2. Okay, so in this case, here sigma y square is 25, so 25 sx square by 36 sy square follows the f distribution with 9 and 11 degrees of freedom because here n equal to 10, m equal to 12. Okay, fine. And here we are interested in the probability of Sx less than Sy. Here Sx denotes the sample standard deviation of group 1, Sy denotes the sample standard deviation of group 2. Okay, so this Sx less than Sy event will be equivalent to Sx by Sy less than 1. This will be equivalent to Sx square by Sy square less than 1. That's why the probability of Sx less than Sy, I can write the probability of Sx square by Sy square less than 1. Now this Sx square by Sy square less than 1 event will be equivalent to, if I multiply 25 by 36 each side, will be, okay, so that's why the probability of this event will be same as probability of this event. So I can write, so the probability of this event equal to probability of 25 sx square by 36 sy square less than 25 by 36 times 1. Okay, now we know that this follows the f distribution with 9 and 11 degrees of freedom, and this will be simplified to 0.694. Okay, so we have this probability of f9, 11 less than 0.694, and because this f distribution is a continuous distribution, so this equality doesn't matter, so still we can write the probability of f9 11 less than or equal to 0.694. So by definition, this is the CDF of f distribution with the 9 and 11 degrees of freedom at 0.694, whose value going to be 0.2966. You can get it from SciPy package like this. Okay, you create f random variable with 9 and 11 degrees of freedom, call the CDF method at 0.694. Okay, then it should return this value. Let me show you. So this is the CDF value of F distribution with 9 and 11 degrees of freedom at 0.694. Okay. In this solution, we did not use given population means mu x mu y. Okay, let me stop now. Thank you.